In this video, we'll go over the simulation exploration of wave interference. We'll click on the Water Waves tab to start. In step 1, click on the image below to begin the simulation. Note that this simulation will prompt you to download and run a Java applet. We'll follow these steps to set up the water wave simulation. Click Add Detector button, then move the detector readout display below the ripple tank. Increase the frequency of the drips by moving the frequency slider to the middle of the range. Move the rotate view slider from the top position to the side position and note the appearance of the water waves from this perspective. Return the rotate view slider to the top position. Step 2, place the detector sensor right under the faucet and make note of the amplitude and frequency on the detector. Move the detector to the middle of the tank, then to the very lower or upper right corner of the tank. Question 2. What effect does increasing the distance from the source have on the amplitude and frequency of the waves? The amplitude of the waves decreased as the detector moved further from the drip source, but the frequency of the waves remained the same. In step 3, change the settings to 2 drips in the right window and give them a separation spacing of 5 centimeters. Place the detector sensor at the bottom of the water wave tank so that it is just to the right of the Show Graph button. Slowly move the detector sensor straight upwards until the detector graph shows no change in the water level, or very small change. Question 3. Why does the water appear to be relatively still at this point? It is because the crests, nodes, from one source, drip 1, are meeting up with the troughs, antinodes, of the other wave source, drip 2, and canceling out each other's effects. This is called destructive interference. Step 4. Move the detector sensor a little further upward until the graph shows the maximum change in the water level. Select one drip from the right-hand panel and notice what happens to the water level on the detector graph. What change did you observe? When one drip was reinstituted, the water waves had noticeably less amplitude. In step 5, reselect 2 drips and notice the level of the water waves. Why does the amplitude of the water waves at the measurement point appear greater? Because at the point of measurement, the crests of the waves coming from one source are meeting up with the crests of the waves from the second source, combining their amplitudes at that point. This is called constructive interference. In step 6, follow these steps to set up the water wave single slit diffraction simulation. Select one drip, if not already selected. Select one slit. Set the slit width to 2.5 centimeters. Set the barrier location to 6.2 centimeters. And place the detector sensor so that it is to the right of the barrier. In step 7, move the detector sensor from the very bottom to the very top of the wave tank. Question 7. As you slide the sensor along the vertical axis, what do you observe? It is observed that the amplitude of the wave emanating from the slit decreases the further above or below the slit the detector is positioned. In Step 8, we'll follow these steps to set up the water wave double slit diffraction simulation. Select one drip if not already selected. Select two slits. Set the slit width to halfway between 0 and 2.5 centimeters. Leave the barrier location at 6.2 centimeters. Set the slit separation to halfway between 0 centimeters and 4.2 centimeters. Make sure the detector is to the right of the double slit barrier. In Step 9, move the detector sensor slowly from the bottom of the water tank to the top. Question 9. What did you observe? It is observed that the waves emerging from the two slits formed a pattern similar to our two drip scenario and constructively and destructively interfered at different points in the wave tank. Let's go on to the Sound Waves tab. Step 1. Follow these steps to set up the water wave simulation. We'll click on the Sound Waves tab at the top of the simulation window. We'll click Add a Detector, unless there is already one present. We'll set the frequency and the amplitude sliders to the middle of their range if not already set. In Step 2, think back to the water drip waveforms with one drip. Question 2. How does what you see when you slide the detector sensor up and down compare to what you saw in the water wave simulation? The waveform appears to have the same behavior for sound waves as they did for water waves. Step 3. Select the one slit option in the right window. Move the detector sensor from top to bottom and observe the interference pattern. What do you observe? We observe the interference pattern behaving the same way as it did for the water wave. Step 4. Now select the two slit option in the right window. Question 4. Thinking back to the water waveforms with two drips, are there any differences in the waveforms as you slide the sensor along the vertical axis? No, the waveforms are the same for water drips as for sound waves. Let's go on to the Light Waves tab. We'll follow these steps to set up the light wave simulation. Click on the Light Waves tab at the top, add a detector, click the Show Screen button, then click the Intensity Graph button, and finally click on the Show Graph button. In Step 2, think back to the water waveforms with one drip. Is there any difference in the waveforms as you slide the sensor along the vertical axis? No, the waveforms are the same for water drips as for light waves. Step 3. Check the Two Lights box in the right window. Move the sensor vertically through the waveform and describe what you observe on the screen, on the intensity screen chart, and the E-field detector scan. What do you observe? We notice that the maximum and minimum interference patterns that correspond to the screen chart waveform for intensity. Step 4, slide the wavelength to the blue portion of the spectrum. What changes do you observe in the intensity screen chart and in the E-field detector? We observe that the intensity of the blue wavelength is less than the red wavelength, and the points of minimum and maximum interference differ. On the E-field detector, the amplitude of the E-field is less than in the blue part of the spectrum compared to the red part of the spectrum. In step 5, select one slit from the right-hand window. Alternate between one light and two lights with the wavelength in red. What changes do you observe on the intensity screen chart, E-field detector, and frequency? We observe the same waveform to the right of the one slit, but notice that the intensity graph and the E-field detector graph both show an amplitude increase with two lights. The frequency remained the same. In step 6, slide the wavelength slider to the blue portion of the spectrum. Question 6. What changes do you observe in the intensity screen chart, E-field detector, and frequency? We observe the same waveform to the right of the one slit, but notice that the intensity graph and E-field detector graph both show an amplitude increase with two lights. Frequency remained the same. We observe that the intensity of the blue light is less than the red wavelength. Step 7. Return to the red spectrum and select one light with two slits. What changes do you observe in the intensity screen chart, the E-field detector, and the frequency? We observe a central max for intensity and E-field amplitude. The frequency remains the same. Step 8. Once again, slide the wavelength to the blue portion of the spectrum. What changes do you observe in the intensity screen chart, E-field detector, and frequency? We observe the same effect as with the red, but the central max and second-order max interferences are observable and uniform. Frequency remains the same. In step 9, return to the red spectrum and select the two lights with two slits. What changes do you observe on the intensity screen chart, E-field detector, and frequency? We observe a central max for intensity and E-field amplitude and noticeable second-order max and min, and the third-order max is trying to appear. Frequency remains the same. In step 10, slide the wavelength to the blue portion of the spectrum. What changes do you observe on the intensity screen chart, E-field detector, and frequency? We observe the same effect as with the red, but the central max and second-order max and min interferences are more profoundly observable and uniform. The frequency remains the same. I hope this video exploration of the simulation for wave interference was helpful.